Good morning, everybody. Welcome to physics today. Got a couple of notes here, and then we'll have an assignment. So this is kind of summing up some of the things that we talked about yesterday. Today what we're going to talk about is FBDs, which is short for free body diagram. Free body diagram. And so why it's called that is the free body part is you're supposed to have in your picture only one thing, and that would be the free body. But really, oftentimes you have more than just that free body. So what you need to do is concentrate on one thing in the picture, and then draw all of the forces that are applied to that body. Okay, so keep in mind, the force is a vector. Vectors have size and direction. The size or the length of the arrow signifies the number, and then the direction is signified by the head. Okay, so types of forces. This is a little bit of a review from yesterday. We have weight, okay, and we said weight is a measure of attraction between two bodies of mass. Okay, so you'll find that in your notes from yesterday if you took notes around yesterday's video. But this is something we don't have from yesterday, and that'd be these abbreviations. So it says, sometimes abbreviated as big W, which is the one that we showed yesterday on the notes. F sub G, so that'd be the force, according to little g, which is the force of gravity. I do this F sub mg, because we talked about weight being equal to mass times little g yesterday, right? And also, little m, little g would be like another way that I might abbreviate weight. Because, you know, weight is mass times little g, so I just put that in there. Okay? So all these things are abbreviations that are fair game that people use for the force weight. Okay? And then these are friction. And we said this yesterday too, it always opposes motion or potential motion. Okay? And then we have two kinds of friction. We talked about this yesterday. We have kinetic friction is when an object is moving. And static friction is when an object is at rest. Most of the time, static friction is larger than kinetic friction for various reasons, unless we're talking about fluid friction. And fluid would be a gas or a liquid. Fluid friction is the opposite. I'll just show you real quickly the relationship for fluid friction and velocity. It's like this. It's exponential. So the bigger your velocity, the much greater your friction is in a fluid. So you might have that idea if you ever stuck your hand out the window of your car, right? That's fluid friction right there in your hand. So, but we won't be dealing with fluid friction. We'll be dealing with contact, or we'll be dealing with surface friction, which is usually less once you get moving. Okay. And then we have tension, which was another one that we talked about yesterday. And what did we say about tension yesterday? We said tension is the force that's transferred through a rope or a rod by something pulling on either end. Okay? Tension is the force that is transferred through a rope or rod by something pulling on either end. Okay? These are the abbreviations for tension. Oops. We have a big T, or force subscript T. Those would be two abbreviations for tension. The tension is going to be a very important idea that we use to study Newton's third law, which we haven't quite talked about yet. Then we have the normal, which comes from that, the normal comes from the framing or the construction term, and the normal means perpendicular to the surface. That's like the original term, before physics took it on. So that's like the first part of the definition of the normal. And then the second part of the definition is the force that a surface applies to an object to keep that object from falling through the surface. And I gave you some examples of that yesterday, how that changes with angle, right? Okay. And these notes are online here too, so if you're not getting all these notes and you're understanding them, you'll be fine. Okay. The force is with us, right? Okay. So this is the force that keeps an object from falling through the surface on which it sits. The normal force is always perpendicular to the holding surface. Okay? And I guess I don't have on here what I abbreviate that is, or what the abbreviations are, but it could be N, it could be force sub N. Those two would probably be the most common abbreviations that I would use. Okay. And yesterday we talked about how that changes with the angle of the ramp, right? So, free body diagram. Okay, so here's a free body diagram. A picture of an object and all of the forces acting on it. Okay, so here's our first example. A box sitting on a level table. Okay, so let's see if I can go to Okay, we have a box sitting on a level table. There's one force that is always there. What is that? Force of gravity, right? Okay, so force, so little g, that's a force of gravity, and it's always going towards the center of the earth. Okay? Now, according to Newton's second law, this thing would be accelerating if that was the only force upon it. Agreed? So there must be another force that's keeping it from accelerating downwards. That's the normal. Very good. Okay? So that would be force sub N, keeping in mind that this and this, those two distances, which are indicated by the length of the arrow, those should be equal. Because if not, then they're not the same number, and then the summation of forces isn't zero, and the thing accelerates. So there's your free body diagram for something sitting on a table. Okay, so the question was, what about static friction? Which is a very good question. So the third...
This sounds so cool in your voice.
So the definition of friction is an opposite motion or potential motion. So you might ask yourself, is there motion or potential motion here? No, there's no potential motion. Why is there potential motion? Well, because of the table. Okay, so that doesn't count. Because that's like a flat on, it's a push right on top. There's no friction in, just pushing straight on it. Right. So, we'll talk about friction a little bit. Does that answer your question? Okay, so this just double checks our what we did. Remember, the forces are vectors, size and direction count. These are the same length. That's right off your notes. So example 2, a box being pulled by a rope and it's frictionless. Okay, so this would be the rope pull. So whatever that is, let's say it's 20 newtons. Okay, now you don't need to put the number on the free body diagram, but that would be the pull of the rope. We still have the force of gravity, right? Okay, so let me just quiz you here. According to my drawing, is the box, what is the box's mass? Equal to, greater than, or less than 2 kilograms? I would say it's less than, because this length here is less than this length. Do you agree? Oh, I'm sorry, I said that opposite. This one is less than this length. And since the length of the vector shows the number, then this has to be less than 20 kilograms, or 2 kilograms. Because 2 times 10 would be 20 newtons. So after explanation of why this must be less than 2 kilograms, because the 2 kilogram mass would have a vector that would be equal in length to a 20 newton vector that we've already showed on here. We can say that there's also got to be what? Why is it not going down to the ground? So there's a normal force. So these two lengths here would need to be equal to each other. These two, right? Okay, is this thing going to accelerate? Yeah, this is going to accelerate with the force of 20 newtons in that direction. Do you agree? Okay, let's go to the next one. Okay, the next one is a box falling in a vacuum. Vacuum is the absence of anything. So a box falling in a vacuum of space, which space actually has some particles in it. Is there anything other than the force of gravity on this box? No. This would be the only force if it's a vacuum. Now, what if there's air friction? If there's air friction, like all friction opposes motion, which means it's totally opposite in direction. So, if this thing is not at terminal velocity, which do you know, understand what terminal velocity is?
The max velocity you can get under resistance.
Yeah. So, some say it's the max velocity you get under resistance, or air resistance in this case. Mathematically, it would be when the force of the air friction is equal to the force of gravity. So there's no acceleration. So if this thing is still accelerating, then we had a force of, fluid, or you could put some A, right? If this thing is at terminal velocity, then this needs to be the same distance, because the summation of forces would be equal to 0 then, because we'd have one in that direction, one in that direction. So this arrow would then change to equal in length, but opposite in direction of the force of gravity. So this would be at terminal velocity. Okay. A wagon being pulled with no friction. Okay, so this is a pretty important one. You gotta look at this. So we got a wagon, right? And it's being pulled without friction. So let's say that this right here, this force is, well, if we're pulling it, what do we label this force? Tension. Because you're pulling on that rope, it's got a force of tension that's applied through this rope, so whoever's pulling it, the tension gets applied to whatever's on the other end of the rope, okay? So look at this. What does everything always have? Force of gravity, okay? So there's your force of gravity. There's no friction, so there's going to be no X forces. Okay, so look at this. The force of normal here now, right? Because this thing has to be pushed up on, otherwise it's going to fall through the surface of the earth. So the force of normal, in this case, is going to be, what is it going to be? There it is. Any problems with that, people? Equal in length to, oh yeah, that is what we said before, right? But now there are other forces at play here. So, what do you think is helping the force normal in this case? Tension, very good. And what specifically, what part of tension okay, is helping the x or the y part. The y part, right? So if we split this into vectors, so this is going to be the accelerating part of tension, but this part of tension is pulling up on the wagon, making it easier for the ground to keep it up. Does that make sense? If I pull hard enough, kids are going to be flying out of the wagon, right? Because I'm going to pull it like it's going to get airborne. In other words, have you ever done that to your little brothers and sisters? Oh my. I didn't expect you to say yes. So if we look at this, okay, we'll say that this is x. We'll say that this is y. Okay. So by default then, this is what? X plus y. Do you agree? So just to clarify, after discussion with my students, x is just a variable. In this case, it's in the y direction, right? And y here is just another variable, which is actually in the y direction too. So thank you very much for that. I understand it can be confusing, but we just need to be taught. There's only two directions that we really consider. So yes, you have a question? A baseball being hit by a bat. Okay, so here's the bats. Here's hitting a baseball. Okay, what does the bat have always? The baseball always has force of gravity, right? Okay. Now in this case, Gm, little mg, force of gravity. Okay. Now, is there a normal on this? Well, depends on the orientation. You wouldn't normally say that this has a normal because it's a swing and a hit. But there would be what? What's going to make this thing accelerate? The force of the bat. So the force of the bat here. Okay, anything else? No. Okay. Let's look at another one here. I'm going to do a couple more that aren't on the notes. Okay, so let's say that this is a ball in free fall, okay, which means there's no air, right? Or, there's no air resistance, we'll just say. The free fall might be used differently, but that would just be the force of gravity. So kids usually screw up because they think, well, geez, why is it going this way if there's only one force? Well, because down here, there was a different force, right? But right now, during the free fall, there's only the force of gravity. Well, let's say that we have air here, okay? In what direction would the air be? Well, the velocity at this point would be at tangent. Do you agree? So that would be the velocity. So that's not part of the free body diagram. But if you know the velocity, you know the direction of friction is going to be what? Exactly opposite, right? So we'll say that this would be then the force of air. Change that color. This would be the force of air, okay? And that would be our free body diagram. Okay. So let's look at another example here. Let's say that I have a rope and another rope, and we'll say that these angles are similar, congruent. Okay. This would be, let's say this is tension 1, and this is tension 2. Okay. Let's say that here's your force of gravity. Okay. right now, what are you thinking about the ropes? Because there's nothing else there. So they're the only thing that can counteract this force of gravity, do you agree? So, if you take this as 2x, or let's put it as y this time, because it's in the y direction. Not that we need to, but 2y. Okay? Then how much y is going to be in this tension, do you think? 1y, right? So we're going to have to, that's not the force, but I'm just putting that there so I know what the, because I'm going to have to form my force vector by things that I know. So this would be 1y here, and then over here would be another y, okay? And there's got to be an x, right? But this thing isn't moving to the left or the right, so what's canceling out this part of the x? The other x, right? Which then we can say this here is our free body diagram in the blue. That would be our free body diagram, and that's why it's formed the way that it is. Any questions about that? Okay, let's do one more. All right. Let's say that we have a rope like this. Okay. We have our force of gravity right here. Okay, so these ropes are going to have to take up that force of gravity. First of all, look at these different tensions. Tension 1, tension 2. Which one do you think is going to be holding this up more? Tension 2, right? Yeah, the biggest thing is kids think that the length of the rope has something to do with the vector. It doesn't. Unless in this case, the length of the rope is, the longer the length, the smaller the tension. Right? Have you ever tried to carry something with somebody? If you're right on top of it, you're lifting a lot more, right? So the best free body diagram for this then would have a larger vector here and a smaller vector here. Okay, and that would be a decent free body diagram, keeping in mind if this is 3y, then this must be how many y? 2y, and then this would be 1y. And then these x's are going to be equal to each other. But the actual free body diagram then is in the red only. But we see what it's formed by looking at the x and y components. Okay, so that will help you get started with your homework. Any questions? Okay, have a good day.